let's look then at some waves. We're going to consider two different waves of different frequencies, omega 1 and omega 2, and these will be angular frequencies we're going to use. And we suppose that the wave velocity v is the same for both of these waves, that it's independent of frequency. So the velocity the wave goes at does not depend on its frequency. Then, in general, we know that the wave vector magnitude k is omega divided by the velocity v. And that's going to be the same for both waves. So that means that the wave vector magnitude for wave 1, k1, is omega 1 divided by v. And for k2 here, the wave vector magnitude for the second wave, it will be omega 2 divided by v. So let's take two such waves of equal amplitudes and add them together. What we're going to get is what we'll see are spatial beats, a kind of a spatial envelope over the underlying wave. So here are the two waves we're going to add together here, this one here, the red one, this one here, the blue one, and what we're going to get as a result is the purple one. And you'll see that the purple one fits under a kind of an envelope that is given by this sketched green line here, the dashed green line. And this envelope moves forward at the same speed as the wave. And we've chosen a velocity v equals 1 for illustration here. And you'll see as a result of that, then numerically the k values are equal to their corresponding omega values. So this wave has a frequency of 0.4 units, the resulting k vector, because we chose the velocity to be numerically equal to 1, is 0.4 units. In the second wave, the frequency is 0.425 units, and correspondingly, the k vector magnitude is 0.425 units. So again, we see the sum of this red and this blue wave giving us the purple wave. And that purple wave behaves as if it had a sort of envelope multiplying it. But that's just the linear sum of these two waves, and this envelope is sort of our spatial beats. Algebraically then, for two waves of different frequencies, so we've got one at frequency now, we'll call it omega plus delta omega, and that will have a wave vector k plus delta k, and another one at frequency omega minus delta omega, and correspondingly a wave vector k minus delta k. We're going to use complex exponential waves here. So as a result, we get a total wave, which we'll just call f of z and t here, that is the sum of these two. So here's our first one at frequency omega plus delta omega and wave vector k plus delta k. And here's our second one at frequency omega minus delta omega and wave vector k minus delta k. Now, we note we've got a common factor here. The common factor would be the exponential of minus I omega t minus kz. So we can pull that out of these two factors here. And the result is that we're left with this expression. But you may recognize that expression. That's really just the cosine of delta omega t minus delta kz. It's multiplied by a factor 2. So this original sum of these two waves at these two different frequencies, we can rewrite just algebraically as a wave at one actually averaged frequency, so the omega, which is halfway between the two extremes, and an averaged k vector, which is also halfway between the two k vectors, multiplied by this envelope here. And this is the envelope we were seeing as our spatial beats. And note that the effective frequency of this envelope is delta omega, and the effective k vector is delta k. So then, with this algebraic form we've just worked out, the cosine envelope multiplying the underlying wave, and we're going to show the real part of this wave here. This is the wave we were just looking at, the red one, the blue one, the sum of the two. Now note here, because k is equal to omega over v, of course that means that v is equal to omega over k, then delta k is delta omega over v, and v is therefore delta omega over delta k. So this cosine part this envelope, is really propagating at a velocity delta omega over delta k. And this part of the wave, the underlying wave, is propagating at a velocity omega over k. So in this case, the envelope and the wave move at the same speed. Just to repeat that, this cosine part, the envelope, will move at a velocity delta omega over delta k. And the exponential wave itself will move at a velocity omega over k. And because those ratios are both the same here, they both move at the same speed. But suppose the wave velocity is different for different frequencies. That is, suppose, for example, the higher frequency wave has a slower velocity than we were expecting. So we have a more than proportionately larger k. Remember that k is omega over v, so if the velocity is slower, v is a smaller number, then k has to be a larger number. That means effectively, because the wave velocity is slower, we're packing more waves into the same physical distance. We'll then get our envelope velocity, which we said was delta omega over delta k, and we're now going to give it a name here. We're going to call this the group velocity, so we put a little g here to show that. And it will not be the same as the underlying wave velocity now. So let's look at that. If the higher frequency wave has a lower wave velocity, so a lower velocity v2, maybe it's now 0.97. Actually, what we've done here is we've chosen that the wave vector here in the second wave, instead of being 0.425, is 0.4375. So actually, that makes the ratio of omega over k for the second wave to be 34 over 35, which is 0.97. So this is a slower wave velocity than the velocity of 1 that we were using before. And of course, our first wave here still has a velocity of 1. Our ratio then of delta omega over delta k is going to be the ratio of the difference between this frequency, 0.425, and that one, 0.4, over the difference between the two k vectors, the difference between 0.4375 and 0.4, and that's 0.0375. Actually, the difference between this frequency and that one is 2 delta omega in our algebra, and the difference between this k vector and that one is 2 delta k. So this is really 2 delta omega over 2 delta k, but the 2's cancel. So this is the ratio of delta omega over delta k is 0.025 over 0.0375, and that is 2/3. So our group velocity is 2/3. The underlying wave, by contrast, moves at the average speed. So that's omega 1 plus omega 2 over 2 divided by k1 plus k2 over 2, which of course is just omega 1 plus omega 2 over k1 plus k2. And in that case, this is 66 over 67, which is 0.985. So the group velocity is 2/3, and the underlying velocity of the wave is 0.985. So now we see that the purple wave is actually moving through the envelope. The purple wave is moving faster than the envelope, and that's what we expect here. The purple wave is moving at a velocity of 0.985. The envelope is moving at a velocity of 2/3, so about 0.667 to 3 figures. And this is the difference between the group velocity and the velocity of the underlying purple wave here. We define group velocity more precisely as the limit of this as delta k and delta omega go to 0. So we call the group velocity d omega by dk. And this concept applies rather generally for the effective velocity of pulses or wave packets in dispersive media. For clarity, we're going to call the ratio of omega and k the phase velocity at a given frequency. So this is the group velocity, d omega by dk, And this one, which you've previously known as just the wave velocity, we'll now call the phase velocity, omega over k. So this phase velocity was the velocity of our underlying purple wave, and this was the velocity of the green envelope, the group velocity.